The night sky has this hidden gallery, a kind of cosmic architecture, and our own Milky Way, it's just one piece of that, one exhibit. There are so many others. This time, we're looking at 30 different galaxy types, and they don't look like our home, not at all. Some are these serene spheres, ancient stars. Others are chaotic, whirlpools really born from collisions. By the end, you start to see the universe differently, not just a collection of similar spirals. More like a workshop, infinite forms. There's a perfect ring of stars, what made that, and ghostly galaxies, almost entirely dark, made of darkness. And I wonder, when you picture deep space, how many of these did you already see in your mind? That hazy band of light has been in our sky for as long as we've been here. It's our home, seen from within, the Milky Way, and its shape is what we picture when we think of a galaxy. A great swirling pinwheel, a central hub of older yellow stars, then a thinner disk with these brilliant blue arms spiraling out. They're traced by dark dust lanes and by glowing pink nebulae where new stars form. It's a barred spiral galaxy. It's magnificent, but the crucial point, the one that frames everything, is that this isn't the universal standard. It's just our local address. Our view is limited. We're embedded deep inside that dusty disk, looking out through a kind of fog. We can't get a clean, top-down picture of our own galaxy. Every image you've seen of the Milky Way as a complete spiral is an artist's interpretation, a reconstruction from painstaking measurements of the stars around us. Our perspective is like being a single grain of sand on a beach, trying to sketch the whole coastline. That bias, that galactic provincialism, has shaped our expectations. For a long time, when we looked out and saw other faint, fuzzy patches in the telescope, we tried to fit them into the spiral model we knew. But the universe is a more inventive sculptor. To see the gallery of forms out there, we have to step outside our own front door. We have to acknowledge that our beautiful, familiar Milky Way is just one design. One entry in a catalogue of cosmic architecture that resists easy classification. This gallery starts with a place where spirals aren't the rule, they're the exception. You see a galaxy that doesn't look like ours. It looks like a huge, fuzzy football made of ancient stars. Those are giant elliptical galaxies. They're the cosmic behemoths. You can think of the Milky Way as a busy city with construction and new neighborhoods. A giant elliptical is more like a vast, quiet retirement community. It's smooth and it glows and it's serene, but the scale is almost impossible to grasp. A good example is Messier 87. It sits at the center of the Virgo cluster. Our Milky Way has a few 100 billion stars. Messier 87 has trillions, and those stars don't orbit in a neat disk. They swarm in every direction. Like a hive of bees with no plan, that chaotic motion creates that featureless, three-dimensional glow. There's almost no free gas left there, no cold dust. The material for new stars was used up long ago, or it was blown away in some furious past, so the light from a giant elliptical is a uniform, golden color. It's the combined glow of countless old red stars. So how does a galaxy get like this? The main theory is one of cosmic violence softened by time. They're thought to be the final products of galactic mergers. Not a gentle dance, a full-on collision where multiple spiral galaxies, each like our own, slam together over billions of years. Their delicate disks get torn apart. Their stars get stirred into that chaotic soup. Their gas clouds collide, and that triggers one last huge burst of star formation before it all settles into this smooth, enormous sphere. These titans often sit at the gravitational center of entire galaxy clusters. They're the anchor, the dominant patriarch. Their immense gravity holds whole communities of smaller galaxies in its sway. They're not building new things, they're the quiet, ancient results, the end product of the universe's most dramatic construction projects. You have these giant galaxies. And then you have these ghosts, just faint smudges of light. They're dwarf ellipticals. They're the opposite of the giants in almost every way, except they're also smooth, shapeless. A giant elliptical has trillions of stars. A dwarf elliptical might have a few million. It's like a metropolis next to a forgotten village, and that village is almost empty. The stars in a galaxy like NGC 147, which orbits Andromeda, they're ancient, they're red, they're spread so thin the galaxy is practically transparent. If you were inside one, the night sky would be profoundly dark, just a handful of faint, old suns in a huge void, no gas left for new stars, no dust. It's a silent system, a fossil. What's compelling is how many there are. They're everywhere. For every majestic spiral or giant elliptical, there are likely dozens, even hundreds of these dwarf ellipticals. Drifting in the dark, they're the most common type of galaxy in the universe. Most are satellites bound to a larger host, like moths around a porch light. Their existence is a puzzle, a quiet one. Are they the building blocks, the original small clouds from the early universe that just never grew, never merged into something bigger? Or are they remnants, something that was once more substantial but wandered too close to a giant, had all its gas ripped away, leaving just this skeleton of old stars? Astronomers see evidence for both stories. They are the quiet, ancient background of the universe, the cosmic substrate. We're drawn to the brilliant spirals, the dominating giants. But in these faint ghosts, we might be looking at the universe's most fundamental ingredients, or its most common end results. Grandeur isn't the only measure of significance. Sometimes the most profound truths are written in the faintest light. Some galaxies aren't ghosts or giants. They're in this perfect, quiet balance, the Lenticular Galaxies. The cosmic hybrids. Think of a flying saucer, a lens of light in the dark. That's the shape. They have that central bulge like a spiral and a huge, thin disk of stars. But the disk is smooth, no grand spiral arms, no pink star nurseries. It looks finished, complete. A classic one is the Spindle Galaxy, NGC 5866. We see it almost perfectly edge-on, a sharp line of dark dust cutting through a glowing, golden lens. It's serene, ancient. Astronomers see it as a missing link. A galaxy caught between two states. It's not a spiral anymore. It lost the fuel for star formation. The interstellar gas is gone, used up making generations of stars. Or maybe stripped away by a gravitational encounter. But it's not an elliptical either. Its stars still orbit in an orderly disk. They haven't been stirred into a chaotic swarm. So a lenticular galaxy is a spiral that ran out of gas. Literally, its star-forming days are over. What's left is that beautiful disk. Now it's full of aging stars. Yellow and red, it's a galaxy entering a long, quiet twilight. Their existence tells a story about galactic life cycles. It suggests a spiral's vibrant, blue-armed youth isn't permanent. It can evolve peacefully into this still and stately form. The transition isn't always violent. Sometimes it's just resources. A galaxy uses up its fuel. And its dynamic structure slowly fades into this elegant, fossilized disk. They show that change isn't always catastrophic. Sometimes it's a gentle settling. A cosmic sigh after eons of brilliant activity. But what if that change isn't gradual? What if it's a sudden, violent hit? The universe has an answer for that too. And it looks almost impossibly symmetrical. A perfect circle of brilliant, young blue stars, and inside a calm, golden core. That's a ring galaxy. It doesn't look like an accident. It looks like a cosmic bullseye, like a piece of jewelry. The most famous one is called Hoag's object. You have this nearly perfect ring of hot, new stars. Just floating there, and at the center, a core of older yellow stars. There's a dark gap between them. It's so geometrically perfect it seems artificial. But it's not. It's the result of one of the most dramatic events you can get, a galactic collision. The main theory is a scenario of incredible precision. Picture a smaller galaxy, maybe a dwarf galaxy, on a path that sends it straight through the center of a larger disk galaxy, like our Milky Way. It's a bullseye hit. This isn't a slow merger, it's not a glancing blow, it's a direct, piercing shot. As that intruder passes through the heart of the disk, its gravity acts like a stone dropped into a pond. It sends a powerful wave of compression rippling outward. Through the galaxy's huge reservoir of gas and dust, this density wave moves through the disk. And as it moves, it squeezes all that interstellar material. That compression triggers a cataclysmic burst of star formation, but the wave is circular. It propagates evenly from that point of impact, so the star formation ignites in a near-perfect ring. The galaxy's own center, it gets violently stirred. But it's not destroyed, it's left relatively undisturbed. Its older stars remain. Now they're surrounded by this dazzling, newborn halo. The intruder galaxy, having done its work, just continues on its way. It leaves behind this stunning artifact. These objects are incredibly rare. They're cosmic snapshots, a single, fleeting moment. That ring of brilliant blue stars is a temporary phase. It might only last a few 100 million years. The stars will age, the ring will fade. What we're seeing is the universe in the act of creation, but it was triggered by destruction. A violent, transformative event, and the result, paradoxically, is one of the most beautifully ordered structures we can find. It reminds you, the cosmos isn't just about slow evolution. Sometimes its most breathtaking art is born from a single, perfect catastrophe. A ring galaxy is a perfect circle, but the ring might not be flat. It could be standing on its end. Like a hula hoop spinning around the galaxy's middle, that's a polar ring galaxy. It doesn't make sense, a disk of stars and gas orbiting over the poles. Perpendicular to everything else, it shouldn't be stable, it shouldn't be there, but it is. NGC 660 is a good example. You have a bright central galaxy, a glowing lens shape, and across it a faint dark band. That's the polar ring. We're seeing it from the side. It's a separate disk of material in this impossible orbit. A 90-degree orbit around the galaxy's core. So how does it form? It's not gentle. The main idea is gravitational theft. A smaller galaxy, maybe a gas-rich dwarf, gets too close to a larger one. The tidal forces are huge. The difference in gravity from one side to the other. It shreds the small galaxy, pulls it apart, but the debris doesn't scatter. It doesn't fall in. The angles and speeds are just right. The captured material gets funneled into this extreme polar orbit. It settles into a new disk, rotating at a right angle to the old one, so the galaxy has two axes of rotation, two different sets of rules, and that makes them more than curiosities. They're like natural laboratories, especially for dark matter. We can't see dark matter, we only know it's there by gravity. In a normal spiral, stars orbit in a thin disk. That motion maps the gravity in that plane, but a polar ring gives a second map. The stars in that vertical ring feel the galaxy's pull from a different direction. By comparing orbital speeds in the main galaxy and the ring, astronomers can map the dark matter halo in 3 dimensions. It's like an X-ray view of the galaxy's hidden skeleton. These impossible structures come from a violent encounter, and they become a window into the universe's biggest mystery, accidents of geometry, revealing the hidden architecture. Some galaxies don't settle into a shape, they break the rules. They're the peculiar ones, the misfits, defined by their refusal to be ordinary. Their shapes are wild, distorted. They look like accidents, and they are. The cause is gravitational interaction. A close encounter, a near miss, the start of a collision. Gravity becomes a sculptor of chaos, pulling and stretching structures into something new. Take the Mice galaxies, NGC 4676. Through a telescope, they don't look like two islands. They look like two comets or mice fleeing from each other. With long, streaming tails, those blue tails are made of millions of stars, gas, and dust, ripped from the main bodies by their mutual gravity. This is a slow-motion event. Hundreds of millions of years, we're seeing the opening act of a merger, an experiment in progress. These peculiar systems are crucial. They show us the process. The tranquil spirals and ellipticals in textbooks are just snapshots, moments of calm in a longer, more violent story. Peculiar galaxies are the chapters in between. They reveal the dynamic, interactive dance of galactic evolution. Gravity isn't just an anchor. In these scenes, it's the ultimate sculptor, twisting and reforming entire islands of stars. It reminds us the universe isn't a static museum. It's a workshop constantly under construction, where even the grandest structures are temporary, arrangements in an endless gravitational ballet. From that gravitational chaos, you get the other extreme, a galaxy that's so faint, so spread out, it almost disappears, like a ghost of a galaxy, and not a small ghost. A huge one as wide as our own Milky Way, but if you were inside it, the night sky would be mostly empty, just a few stars against this deep, black void. That's an ultra-diffuse galaxy. It's this strange contradiction, a structure on the scale of a galaxy made with almost nothing. The numbers don't make sense. Take Dragonfly 44, found only a few years back. It stretches about as far as the Milky Way, 60,000 light-years, but it has maybe 1% of the stars. 1%, it's a skeleton, a cosmic outline drawn in the faintest line, so dim it gets lost in the sky's own glow. That's why we never saw them. Our telescopes looked for bright, compact objects. These are the opposite. They're these see-through mysteries. How they form is a real puzzle. How does something that big not collapse? How does it stay so puffed up, so thin? One thought is they're failed galaxies. Early on, a cloud of gas and dark matter starts to collapse, to make stars, but then something happens. Maybe a blast of radiation from nearby, bright young galaxies. It blows the gas away, starves the whole system, star formation just stops, and you're left with this huge dark matter halo, with just a scattering of old stars frozen in that spread-out state. Another idea is more violent. They could be normal galaxies that got torn apart, stretched and puffed up by repeated gravitational encounters, their stars scattered into this vast, thin cloud. But the biggest mystery isn't just the stars, it's what they say about the invisible stuff, dark matter. Measurements of Dragonfly 44's gravity show something wild. Even with almost no visible matter, it doesn't fly apart, it holds together. The math says it has as much dark matter as the Milky Way, a ghostly galaxy with the weight of a giant. But that weight is almost all hidden. This changes things. It says dark matter doesn't always clump the same way. It can make these huge, fluffy halos. And for some reason, they just never pulled in enough gas to become a bright galaxy. They're a pure form of the universe's hidden frame, a sign that what we see is just the decoration. The faintest bit of light on an immense, invisible structure. A galaxy doesn't only fade or get stretched out, it can also erupt. There's a type called a starburst galaxy, where the whole system gets caught in this cosmic fever. A frenzy of creation so intense it almost destroys itself. Messier 82, the Cigar Galaxy, is a good example. From a distance, it looks like a ragged cigar of light. But that light shows violence. Inside, stars are being born hundreds of times faster than in our Milky Way. Whole clusters of massive blue stars ignite together, lighting up huge clouds of gas from within. It's not gentle, it's a firestorm. The energy from all those new stars, especially the big ones that quickly go supernova, heats the gas around them to millions of degrees. It drives colossal winds, blasting material out of the galaxy in two huge jets. You can see filaments of glowing gas shooting out perpendicular to the disk, like smoke from both ends of a lit cigar. This is a galaxy burning its fuel recklessly, spending its entire interstellar savings in one spectacular binge. And what starts this? Almost always a gravitational disturbance. A close encounter or a merger. For Messier 82, it's its massive neighbor, the spiral Messier 81. Their gravitational dance stirred up the deep gas inside the cigar galaxy, compressing it and triggering this chain reaction of starbirth. It's a brilliant, unsustainable explosion. A starburst galaxy is in its glorious, tumultuous prime, but that prime can't last. In just a few tens of millions of years, a cosmic blink, it will have turned most of its gas into stars. The most massive of those stars will have already died as supernova. What's left is a population of younger stars and a galaxy gone quiet, maybe even gas-poor after the storm. They show the universe's capacity for explosive change, not from a single impact but from an internal fervor. A chain reaction of birth that reshapes the galaxy from within and scatters its substance into the void. Even the brightest stardust has to go out, the fuel gets used up, the show ends, but in the quiet parts of space, in what looks like nothing, you find another kind of fire. Not the big, sprawling fire of a major galaxy. It's the sharp, concentrated flame of something just starting. These are blue compact dwarf galaxies, the young ones. Think of a galaxy so small and faint you'd miss it, just a smudge, but that smudge shines with a hard, electric blue. That's the sign. It's the light from thousands of massive stars, young and hot. Stars that burn fast and die young. These little galaxies aren't quiet places. They're frantic nurseries. All their energy goes into one thing, this single, spectacular burst of making stars. There's a famous one called Zwicky 18. For a long time, astronomers believed it was one of the youngest galaxies we'd ever seen. Its light seemed to show almost no old stars. Just this brilliant blue population. It looked like it was having its very first major burst of star formation, a cosmic debut, a galaxy being born in a universe that was already 13.8 billion years old. That idea got refined. It does have some older stars, but it's still a powerful example. It shows us what the first galaxies might have been. In the early universe after the Big Bang, everything was dark. Just huge clouds of hydrogen and helium. Then gravity started pulling those clouds together. The first things to ignite, to turn on the lights, were probably a lot like this. Small, messy clumps of gas suddenly collapsing and lighting up with their first generation of stars. A blue compact dwarf is a local echo of that first dawn. They are tiny, often just a few thousand light years across. They don't have much mass, but they are powerhouses. Their rate of making stars for their size can be far greater than our own Milky Way. They are all engine. Studying them is like finding a living fossil, a window into a time when the universe was young and dark, just starting to paint itself with light. They remind you that grandeur isn't about size. Sometimes the biggest revolutions happen in the smallest, most quiet places. A faint blue smudge can hold the secrets of how it all started. That faint blue smudge is one extreme, but then there's the other extreme. Ancient, huge galaxies that are almost invisible. There's a whole class of them. Low surface brightness galaxies, they're like faint murmurs. Their starlight is spread so thin it gets lost in the natural glow of the night sky. For decades, our telescopes looked right through them. We only saw the bright things, the spirals, the ellipticals. These were the ghosts hiding in plain sight. The best example is Malin 1. At first glance, it looks unremarkable. Just a small, bright center, but that's an illusion. The truth is, Milky Way is one of the largest spiral galaxies we know. Its disk stretches over 650,000 light-years. That's more than 6 times the width of our Milky Way, but its light is so diffuse, so thin, we needed special techniques just to see it, a ghostly giant. A whisper made of stars, these galaxies exist in a state of quiet. They're dominated by dark matter. The visible stars are just a faint tracer of a huge, invisible halo. And because everything is so spread out, the density is too low for much star formation. There's no frantic starburst, it's slow, steady, almost dormant. They're like cosmic reservoirs, holding vast amounts of material in a kind of peaceful equilibrium. Their discovery changes things. It tells us our map of the universe is incomplete. It's biased. We've been counting the bright city lights and missing the vast, dark countryside. If something as colossal as Milky Way could hide for so long, how many more are out there? The universe might be filled with faint giants, a hidden population quietly spinning. It forces a question: are the bright, star-filled galaxies the rule? Or are they just the loudest voices in a cosmic chorus made mostly of whispers? The faintest giants aren't the only ghosts out there. Some of the deepest mysteries are much closer to home. Orbiting our own Milky Way, there are these dwarf spheroidal galaxies. They're like faint fireflies caught in the glow. They're the ultimate cosmic understatements. The Draco dwarf, for instance, through a telescope, it's barely a smudge, just a faint, shapeless cloud, a few million ancient red stars. It looks insignificant. A wisp, but that's a complete illusion. The truth inside these objects is one of the most startling facts in astronomy. A dwarf spheroidal galaxy isn't held together by its stars. Those visible points of light are just tracers, accidental, like tossing a handful of dust into a hurricane. The dust shows you the wind's shape, but not its power. Over 99% of the mass in a galaxy like Draco is invisible. It's dark matter. The stars we see are just markers, floating in a vast, deep sea of this mysterious mass. The numbers are staggering. The gravitational pull needed to keep those stars from drifting apart implies a density of dark matter so high it's hard to grasp. These tiny, faint satellites are, by proportion, the most dark matter-dominated objects we know of in the entire universe. That makes them more than curiosities. They're perfect natural laboratories. Because they're so close and so rich in dark matter, they've become prime hunting grounds. Scientists look for the faint signals that might arise if dark matter particles, swirling in that dense halo, occasionally annihilate one another. But their significance goes deeper. Astronomers now think dwarf spheroidals aren't just satellites. They're likely the fundamental building blocks of everything. The prevailing theory says that in the early universe, vast halos of dark matter began to clump. Smaller halos holding pockets of gas were the first to ignite with stars. These were the primordial dwarf galaxies. Over billions of years, gravity drew them together. They merged again and again, assembling the majestic spirals and giant ellipticals we see today. So our own Milky Way isn't a singular creation. It's a cosmic metropolis built from the ruins of thousands of these ancient dark dwarfs. Their stars were absorbed. Their identities lost, but a few survivors, like Draco, remain in orbit. Silent, dark relics of the universe's first structures. They're the fossils of galaxy formation itself. So when you look at that faint smudge, you're not looking at a failed galaxy. You're looking at a seed, a primordial fragment, one of the original pieces. The pieces from which everything grand was built. The universe isn't just relics and grand designs. Sometimes it's a glorious mess. A galaxy can be a chaotic scribble on the dark. An irregular galaxy, no spiral arms, no smooth elliptical glow, no defined shape. They look like cosmic accidents, bright, messy blobs, and the most famous one is right in our backyard. The Large Magellanic Cloud, it's a satellite of the Milky Way. You can see it as a faint, hazy patch in the southern sky. Through a telescope, it's all disorder. A tangle of pink nebulae, dark dust lanes, brilliant blue star clusters. It looks like a galaxy caught in the act, creation or maybe destruction, all raw material and frantic energy. So why does a galaxy stay messy? There are two main paths. The first is primordial, some small clouds of gas and dark matter in the early universe. They never had enough spin. They never flattened into a disk. They stayed puffy and chaotic. Galaxies that skip the elegant design phase. The second path is more dynamic. A normal small spiral galaxy can have its structure wrecked by a close encounter. The tidal forces from a massive neighbor, like the Milky Way pulling on the large Magellanic Cloud. It stirs it up, distorts the shape, disrupts the rotation. Triggers bursts of star formation that light it up in a chaotic pattern. That's likely the story of our nearby neighbor. Its messy, brilliant state is a result of its gravitational dance with our home galaxy. And this lack of grand structure is what makes them vital. In a majestic spiral like the Milky Way, star formation is complex, governed by density waves, magnetic fields, the orderly rotation of the disk. The raw physics is hard to see, but in an irregular galaxy, it's all laid bare. These systems are often gas-rich. Their simpler, turbulent environments give a clearer view. Almost like a laboratory, the fundamental recipe for making stars. You see giant clouds of gas collapsing under their own gravity. You see the fierce radiation from newborn stars carving bubbles and pillars in the material. Star formation, unpolluted by complex galactic dynamics. They are the universe's workshops, where lighting up the dark happens in its most direct form. In their beautiful chaos, you see the elemental forces of creation at work. Even a galaxy that's chaotic and brilliant, like the large Magellanic Cloud, still has a calm heart. It's just a collection of stars, but for the next type, that calm is an illusion. The heart is a furnace. Those are Seyfert Galaxies. At first glance, they look like normal spirals. Beautiful, serene pinwheels, but if you point a telescope at their center, especially one that sees X-rays or radio waves, the data shows something terrifying. The nucleus, the very core, is shining with the power of billions of suns, all from a region smaller than our solar system. It's a point of light so intense it can outshine the combined light of every other star in that galaxy. That's not a cluster of stars, that's the signature of a supermassive black hole feeding, a monster at the dinner table. The classic example is NGC 1068. A beautiful spiral seen face-on. Its arms are traced with dust. It looks peaceful, but its core is one of the brightest, most studied active nuclei in the sky. Here's what's happening. Imagine a black hole with the mass of millions, even hundreds of millions of suns. It sits in the galactic center, and around it, a vast, flat disk of gas and dust spirals inward. This isn't a calm flow. It's a chaotic, violent whirlpool. As material in this disk rubs against itself, it heats to millions of degrees. It glows fiercely across the whole electromagnetic spectrum. And before the last of the material crosses the event horizon, it releases a staggering fraction of its mass energy as light. That's the engine, a supermassive black hole actively consuming its surroundings. What makes Seyfert special and so crucial is their scale. They're the lower luminosity class of active galaxies. The black hole is active, but it's not so overwhelmingly bright that it drowns out the host galaxy. We can still see the spiral structure clearly. That gives astronomers a priceless opportunity. They can study the relationship between the host galaxy, its stars, its gas, its spiral arms, and the behavior of the central engine. Is the black hole's activity triggered by a fresh influx of gas, maybe from a galactic merger or a spiral arm channeling material inward? And then, does the intense radiation from the nucleus blow gas away, quenching star formation, regulating the galaxy's growth? Seyfert Galaxies suggest a feedback loop. The galaxy feeds the black hole, and the black hole, through its furious output of energy, governs the future evolution of the galaxy. It's a symbiotic relationship, a violent one. They show us that a brilliant, serene spiral can harbor this unimaginable power at its heart. A quiet neighborhood with a power plant in the basement that could light up a continent. That furious heart has an even more dramatic form. When a supermassive black hole is feeding at an extreme rate, it doesn't just glow, it erupts. It can launch two beams, opposing beams of pure energy and matter, moving at nearly the speed of light, straight out into the space between galaxies. These are the cosmic jets of radio galaxies, and the structures they create are on a scale that's hard to grasp. The classic example is Cygnus A. In optical light, it looks like a normal, distant elliptical galaxy. Just a fuzzy blob of old stars. But if you point a radio telescope at it, the view changes completely. You see two colossal, glowing lobes of radio emission. They sit on opposite sides of that central galaxy, and together they stretch over 1 million light years. That's 10 times the width of our own Milky Way. The galaxy itself is just a tiny dot at the very center of this vast, dumbbell-shaped thing. Those lobes are the endpoints, where the jets, after traveling for hundreds of thousands of light years, finally slam into the thin gas that fills intergalactic space. The impact is a collision. It heats the gas, accelerates particles, and makes those regions glow brilliantly at radio wavelengths. The jets themselves are narrow. Focused beams, they're born from the twisted magnetic fields and the intense pressures right around the black hole's poles. And they channel a staggering amount of the energy from all that infalling material. This energy isn't light, it's a torrent of electrons and other charged particles moving at relativistic speeds. These galaxies show that a black hole's influence isn't confined to its home galaxy. It can reach out, it can sculpt the environment on an intergalactic scale. The jets inject enormous energy into the space between galaxies. They heat it, they stir it, and they prevent that gas from cooling and falling into other galaxies to form new stars. They act as cosmic regulators. A single active black hole can dictate the growth potential for an entire galactic neighborhood. The lobes they create are among the largest single, coherent structures we can see in the universe. They are monuments to power, temporary monuments on a cosmic timescale. They might shine for 100 million years before they fade, but while they last, they are a brilliant signature. A reminder that the quietest-looking galaxy, just a simple sphere of ancient stars, might be the anchor for a pair of energy beams that could stretch from our galaxy to Andromeda and back again. Imagine that jet isn't pointing out into empty space. It's aimed right at us, a cosmic lighthouse, and we're standing in the beam. That's a blazar. It's the most violent, most energetic view you can have of an active galaxy. The name comes from the prototype BL Lacerti. It was first thought to be a variable star, a point of light that flickered, but it wasn't a star. It was the core of a giant elliptical galaxy, billions of light years away, shining with impossible intensity. It's all about orientation. In a radio galaxy, you see the jets from the side. You see the huge lobes they create. But in a blazar, one of those relativistic jets is aimed almost perfectly at Earth. We're looking straight down the barrel. That alignment changes everything. The light from that jet gets boosted by relativistic effects. The radiation is concentrated, amplified, and beamed right at our telescopes. The result is the brightest, most variable objects we see. They flicker not over years, but over days, even hours. They shine across the whole spectrum. From radio waves up through visible light into X-rays and all the way to the highest energy gamma rays. The gamma ray output is staggering. A single blazar can outshine the entire Milky Way by 1,000 times, and all that energy comes from a region smaller than our solar system. The engine is the same as in a Seyfert or a radio galaxy, a supermassive black hole spinning fast with a monstrous magnetic field. Matter falls in, gets torn apart, and a fraction gets channeled and accelerated along the black hole's magnetic poles. But because we're in the beam, we see the raw, unfiltered output of that acceleration. It's like looking into the exhaust of a cosmic rocket engine. Studying them is like a front row seat to the most extreme physics. The jet acts as a natural particle accelerator, far more powerful than anything we could build. By watching how their light changes, we probe the structure of the jet itself. We learn about the magnetic fields that confine it and the unimaginable energies at play just outside the event horizon. They're not just curiosities. They're probes, beacons that let us study the fundamental limits of physics in an environment we can never visit, but whose brilliant, aimed light travels across the cosmos to tell its story. That beam from a Blazar, it's a look into the past, a monster in its prime. But to see how old these monsters really are, you have to look back, way back. To the farthest edges of everything. That's where you find quasars, the brightest things in the whole universe. They make today's brightest active galaxies seem dim. A single quasar can shine brighter than a trillion suns, and it all comes from a space smaller than our solar system. For years after we found them, they were just points of light. Incredible, confusing points. The galaxy around them was invisible, washed out by that furious core. We knew they had to be inside galaxies, but what sort? The answer, now that we can block that brilliant center, is usually something massive and messy. A violent place. The host galaxy for an ancient quasar is often a giant elliptical galaxy, still forming. It's in the middle of a huge merger. You can see the warped shapes, the tidal tails, these chaotic piles of gas and dust. It's the ultimate cosmic construction site. And right in the middle of all that chaos, the supermassive black hole is eating. That's the quasar phase, a short, hyper-bright period in a galaxy's life. Maybe only 10 million years, 100 million, a cosmic blink. But during that blink, the black hole is consuming enormous amounts of gas, driven to it by the galactic collision. It shines with the power of 100 normal galaxies. This tells a deep story about the early universe. It shows that building the giant galaxies, the big ellipticals that rule clusters, and the growth of their central black holes, they weren't separate things. They were tied together. The same violent mergers that put together the stars of a giant galaxy also sent a flood of fuel straight into the black hole. The black hole and the galaxy grew up together in a fierce, symbiotic dance. The quasar's incredible radiation would have blasted everything around it, heating gas and driving powerful winds. That probably played a key role in deciding the galaxy's final size. It's a feedback loop written in light across billions of years, so a quasar isn't just a brilliant point. It's the birth cry of a cosmic giant, a brief, blinding flash that lights up the most important construction project in the early cosmos. The monsters weren't just living in galaxies. They were building them. Not every collision leaves a bright core or a perfect ring. Some leave something quieter, a kind of ghost story written in starlight. You look at an elliptical galaxy and you see 3923. It looks smooth, a golden sphere of old stars, but if you process the image, pull out the faint details, something appears. Delicate shells, dozens of them, they ripple out from the center like rings in a tree trunk or the layers of an onion. These aren't spiral arms, they're not active regions. They're faint arcs made of stars, they're echoes. The galaxy is a shell galaxy, and the shells are fossils, the remains of a smaller galaxy that was eaten. The process is a slow digestion, gravitational. Billions of years ago, a smaller galaxy, maybe a dwarf spiral, wandered too close to this giant elliptical. The tidal forces, the difference in gravity from one side to the other, started to stretch it like pulling taffy. It didn't just crash, it was torn apart. Star by star, its structure was shredded, but its stars weren't just absorbed into the swarm. They were flung into specific orbits, oscillating orbits. Think of a stone dropped in a pond. The ripples move out, but here the ripples are stars, and they don't move. They're stationary, density waves. As the stars from the victim galaxy orbit the core, they slow down at the farthest point. They're apocenter, they spend more time there, so over eons these points of pores build up. A higher density of stars, we see that as a faint shell, a sharp-edged shell. Each shell is a different family of orbits, a different set of stars from the disrupted galaxy, all pausing at the same distance. It's a snapshot, a gravitational process frozen in time. That makes a shell galaxy an archaeological site, a cosmic one. By mapping these faint layers, astronomers can do forensics. They can count the shells, measure their spacing, their brightness. From that, they can run the clock backward, estimate when the merger happened, deduce the angle of the collision, even get clues about the size and type of galaxy that was devoured. It's a way to read a history that ended billions of years before our sun formed. These quiet, layered giants show something. Not all galactic violence leaves a brilliant, chaotic mess. Sometimes it leaves just these perfect, faint ripples. In a sea of stars, a silent testimony to a long finished feast. The shape of an elliptical galaxy is smooth, serene, but at its heart there's a story. Take a giant elliptical like Messier 87. At its center, you see a region where the starlight forms a kind of shallow bowl. The density of stars drops as you reach the very middle. It's a core, a place that's been swept clean. Now look at a much smaller elliptical, a dwarf elliptical. Its starlight just gets brighter and brighter, right to a sharp, dense peak. There's no dip, it's coreless. That subtle difference in the center tells two different life stories. The core in a giant elliptical is a gravitational scar. It's the work of a binary pair of supermassive black holes. When two large galaxies merge, their central black holes sink to the new center. They begin to orbit each other. As they swing around, their combined gravity acts like a slingshot. Any star that ventures too close gets a violent kick. It's flung out of the central region, sometimes ejected from the galaxy entirely. Over billions of years, this process scours out the core. It creates that shallow, star-poor region. The black holes may eventually merge, but the evidence of their dance remains. It's written in the missing stars. The smaller, coreless ellipticals tell a quieter tale. They likely never hosted a pair of such massive black holes. Their formation was gentler. Maybe they were born from the collapse of a single gas cloud, or built up slowly from many small mergers that didn't involve a dramatic black hole binary. Their stars settled peacefully toward the center, creating that smooth, dense peak of light. No great slingshot event ever cleared them out, so by measuring the light profile at a galaxy's heart, astronomers can read its past. A core is a signature of a violent, major merger between two hefty galaxies. A coreless center suggests a more peaceful upbringing, or an origin from smaller, less dramatic building blocks. It's a fundamental dichotomy. The giant, dominant patriarchs of galaxy clusters bear this central scar from their brutal construction. The smaller, quieter galaxies retain their pristine, dense hearts. The universe records its history in the subtle details of light at the very center of things. Our spiral arms are large and defined, but that's not the only shape a galaxy can take. Some spirals appear softer, almost blurred. Their arms aren't long, continuous lines. They're broken into countless brilliant pieces, like tufts of cotton scattered on dark velvet. These are flocculent spirals. Flocculent means woolly. NGC 2841 is a clear example. Seen face on, it's a pinwheel, but when you look closer, the spiral is made of many short, feathery sections. Bright blue star clusters, pink nebula knots, linked by faint dust bridges. It looks like embroidery in starlight. The pattern is everywhere, but it never settles into 2 or 3 main arms. It's a spiral of many voices. This difference in look comes from a difference in physics. In a grand design spiral like ours, the arms aren't fixed groups of stars. They're density waves, like a traffic jam moving down a highway. Stars and gas enter the wave, get compressed, form new stars, and then leave. The wave stays. It's a galaxy-wide pattern, often shaped by a central bar or a nearby galaxy. It's an organized, lasting rhythm, but in a flocculent spiral, there's no single dominant wave. The spiral structure is local, temporary. It comes from instabilities inside the disk itself. Think of weather on a planet. Storms form, grow, and fade. They make local cloud patterns, but there's no planet-wide storm system. In one of these galaxies, part of the disk becomes unstable. A giant gas cloud collapses under its own gravity. That collapse starts star formation. The bright, short-lived blue stars that are born light up that region. They make a bright patch, and as the disk rotates, shear the difference in speed between the inner and outer parts stretches that patch. It pulls it into a short, feathery arm, but the arm isn't permanent. The massive stars die quickly, the patch fades, and new instabilities light up somewhere else. The overall effect is a soft, fragmented spiral, a pattern from countless local events, not a single galactic conductor. So these fuzzy spirals show a different way for a rotating disk to exist. Gravity and rotation can create order in more than one way. Without a strong bar or a gravitational partner to organize it, a galaxy's disk can still find a voice. A murmuring, fragmented voice. It's a quieter, more self-organized kind of spiral. It reminds us that even within one category, the spiral galaxy, the universe has endless variation. The grand design is spectacular, but so is the soft, woolly whisper of a flocculent disk, painting its own transient masterpiece in the dark. The grand design spiral galaxy. That classic shape, the cosmic pinwheel, it's drawn in starlight with this perfect symmetry. The arms aren't broken or patchy. They're 2, sometimes 3, sweeping arcs. These majestic highways of light that wrap around the core in a near-perfect spiral. If you tried to draw a galaxy from memory, this is the shape you'd probably make. And the best example is up in the northern sky, locked in a gravitational dance, the Whirlpool Galaxy, Messier 51. Through a telescope, it's breathtaking. You see this brilliant core anchored by a subtle bar, and from that core, 2 grand luminous arms unfurl. They are traced by the sapphire blue of young star clusters and the soft pink glow of vast hydrogen nebulae. Places where stars are born, dark lanes of cosmic dust weave through the arms like intricate lace. That dust highlights their 3-dimensional structure. It's a portrait of cosmic order on an unimaginable scale, but that order isn't static. It's a dynamic pattern born from rhythm. The leading theory is the density wave theory. Think of a traffic jam, but on a celestial freeway. The spiral arm itself isn't a fixed group of stars. It's a region of higher density, a wave of compression. It moves through the galaxy's disk more slowly than the stars and gas do. When a cloud of interstellar gas enters this slow-moving wave, it gets squeezed. Compressed, that compression triggers collapse. The gas clouds collapse and new stars ignite. The most massive stars, the brilliant blue ones, they light up immediately. They define the arm's bright ridge. They live fast and die young. They often explode as supernova before they can even leave the arm. So the spiral arm we see is essentially a stellar nursery. A propagating wave of birth. The stars themselves pass through it, but the pattern of light, the pattern of creation, it remains. What creates such a perfect 2-armed pattern? Often it needs a partner. For the Whirlpool, its beautiful symmetry is linked to its small companion galaxy. NGC 5195. The gravitational tug from that passing neighbor is thought to have set up the initial density wave. Like a stone dropped in a pond, sending out perfect ripples, without that interaction, the whirlpool might have stayed a more fuzzy, flocculent spiral. The companion acts as a conductor. It imposes a clear rhythm on the chaotic disk. In other grand design spirals, the internal structure can do it. A strong central bar can funnel gas, organize the flow. It creates the same stunning effect. These galaxies are more than beautiful. They're cosmic clocks. By studying the tightness of their spiral arms, astronomers can estimate the galaxy's rotation rate. Its mass, tighter wound spirals suggest a different history of rotation and density than the more open, sprawling ones. The grand design spiral is a temporary equilibrium, a beautiful balance between the gravity that holds the galaxy together and the rotation that wants to fling it apart, and an external or internal force that gives it a clear, singular voice. It's gravity's most eloquent poem, written in light, gas, and dust across 100,000 light-years, a reminder that even in the vast chaotic cosmos, patterns of profound beauty can emerge. And hold for a little while that perfect spiral shape. It's often anchored by something else, a straight line of stars cutting right through the galaxy's heart. That's a bar, and we're in one. The Milky Way is a barred spiral. It's a crossroads, a central hub, where the traffic of the universe gets redirected. Take NGC 1300. It shows this structure, a bright, straight bar of older, yellow stars across its core, and from the ends of that bar, two spiral arms sweep out. It's not a gentle curve from the center. It's a hard turn. The bar organizes things. It manages galactic resources like a cosmic funnel. In a simple spiral, gas clouds orbit on circular paths. It's orderly but slow. The gas might never make it all the way in to feed star formation at the core, but at a bar, that straight structure has its own gravity. And that gravity doesn't follow circles. It creates orbital resonances, gravitational signposts that direct the flow. Gas clouds orbit. They encounter the bar's pull. It nudges them. It takes some of their angular momentum, their orbital energy, and that lost energy lets the gas drift inward. The bar acts like a pump, a conveyor belt. It channels interstellar gas from the outer disk down those stellar highways right toward the center. This inward flow does two big things. First, it can trigger intense starbursts right in the nucleus, creating a nuclear star cluster, a dense, brilliant knot of new suns. Second, and maybe more dramatic, it can feed the supermassive black hole that's probably there. A steady trickle of gas delivered by the bar could be what keeps a central black hole quiet but fed, or maybe triggers occasional outbursts, so a bar isn't just a shape. It's a phase, a dynamic instability that forms in a mature disk galaxy. As stars orbit, their collective gravity can sometimes organize into this elongated, stable structure. Once it forms, it changes everything. It reshapes the gravitational landscape of the entire inner galaxy. It accelerates evolution by funneling fuel toward the center. Many astronomers think most spiral galaxies go through a barred phase at some point. The bar might even be temporary. It can dissolve over time, maybe overwhelmed by the chaos it creates at the center, only to possibly reform later. Our home galaxy, with its own subtle bar, is in the middle of this bustling, dynamic phase. We live in a system that's actively channeling resources inward, driving its own evolution from within. The barred spiral built its own internal highway, directing the flow of cosmic material toward a central destiny. A barred spiral still has fuel. It's vibrant, full of color. Now imagine that galaxy drained. The spiral arms are still there, just faint lines, but the bright blue knots are gone. The pink nebulae are gone. The color fades to a pale, uniform yellow. That's an anemic spiral, a galaxy growing faint, and you find it not in some quiet cosmic countryside, but in the dense, crowded heart of a galaxy cluster. Where it meets a silent, relentless force, the problem is fuel or the lack of it. The lifeblood of any spiral is its reservoir of cold, neutral hydrogen gas. That's the raw material for new stars. In an anemic spiral, that reservoir is empty, the gas is gone, and without it, star formation stops. The massive blue stars that give the arms their color burn out, and they aren't replaced. All that's left are the older, longer-lived yellow and red stars. The spiral pattern becomes a ghost, a faint imprint like a photograph left in the sun too long. So what takes the gas, the environment? In the center of a massive galaxy cluster, the space between galaxies isn't empty. It's filled with a superheated, thin gas. This intracluster medium can be millions of degrees. When a spiral falls into such a cluster, it doesn't drift in peacefully. It plunges in at tremendous speed. And as it moves, it rams into this searing intergalactic fog. That effect is called ram pressure stripping. It's like driving a car through a heavy rainstorm with the windows down. The rain doesn't just hit the windshield, it floods the interior violently. For the galaxy, the rain is that hot, thin gas, and the interior is its own cooler, denser hydrogen clouds. The force of the impact is overwhelming. It doesn't gently push the gas, it rips it away. It scours the galaxy's disk clean of its star-forming fuel. What you're seeing is a transformation in progress. The anemic spiral is caught between two states. It hasn't yet lost the elegant structure of its disk. The stars are still in their orderly orbits, tracing those faint spiral arms. But it has already lost the ability to create. It is becoming what astronomers call red and dead. Its destiny is likely to become a lenticular galaxy. That smooth, lens-shaped hybrid, the anemic spiral, is the middle chapter of that story. A vibrant spiral enters the harsh urban center of the cluster, has its lifeblood stripped away by the crowd, and slowly fades into a quiet, passive state. These faded beauties are tragic in a cosmic sense. They show how environment dictates fate. A galaxy can be born with all the potential in the universe, but if it finds itself in the wrong neighborhood, that brilliant future can be quietly, systematically erased. But in that destruction, something new can form. Those long tails you see from colliding galaxies, they're not just debris. They can become cradles. Inside those streams of stars and gas, dense knots sometimes pull themselves together. And they ignite. These are tidal dwarf galaxies, entire new islands of stars born from a cosmic wreck. Think of the Anemic galaxies, two spirals merging. Between them, you have these vast arcs, tidal tails stretching for hundreds of thousands of light years. And along those tails, like beads on a string, you can see bright blue clumps. Each one is a tidal dwarf galaxy forming right now, from material ripped out during the collision, creation from chaos, a second-generation galaxy built from the ruins of its parents. What makes them unusual is what they're made of, or what they're missing. In our standard model, every galaxy should be anchored by a massive halo of dark matter. That invisible scaffold draws in the gas, provides the gravitational glue, but a tidal dwarf forms from the visible stuff, the gas and stars, that was already in the galactic disks. That material gets flung out into the tidal tail, and if a knot is dense enough, its own self-gravity can cause it to collapse and start forming new stars. The dark matter halo of the original galaxies stays with the main wreckage. It doesn't get flung out into the tails the same way, so these newborn dwarfs are thought to be made almost entirely of normal matter. They are, in a sense, pure galaxies, assembled from the luminous stuff alone. That creates a puzzle. If they have little to no dark matter, how do they hold together? Their own self-gravity from stars and gas might be enough if they're dense enough, but they challenge a core idea. That dark matter is a non-negotiable prerequisite for a galaxy. Here, gravity found another path. It took the raw materials from a disaster and assembled something new by a different set of rules. They are short-lived experiments. Over time, many will likely fall back into the larger merged galaxy or drift apart, but for a while they shine as independent entities, proof that the universe can write new rules in the margins of old ones. Testaments to resilience, showing that even in the most violent endings, the conditions for a new beginning can unexpectedly arise. A galactic core, separated from the rest of its galaxy, would look like this. A dense, brilliant knot of stars just sitting alone in the void. That's the compact elliptical galaxy, a city of stars with no suburbs, all crushed into this furious point of light. The classic example is Messier 32, that bright companion you see next to the Andromeda Galaxy. Through a telescope, it's just a small, smooth glow. But the numbers behind it are staggering. It packs something like 2.5 billion stars into a sphere maybe 8,000 light-years across. The density of stars at its center is immense. If you were on a planet near that core, your night sky wouldn't be dark. It would be this perpetual twilight, lit by thousands of stars, each as bright as Venus, all crammed together. Their origin is a puzzle. One main theory is about gravitational violence stripped down to the basics. You start with a normal spiral or elliptical galaxy, maybe one even bigger than M32, and it drifts too close to a true giant like Andromeda. The tidal forces, the difference in gravity, they act like a cosmic sculptor. They don't just pull off loose gas. They can systematically strip away the galaxy's outer layers, the diffuse halo of stars, the tenuous outer disk. What's left behind after this gravitational peeling is just the dense, tightly bound core, the very heart of the original galaxy, now orphaned. So in this view, M32 isn't a distinct type of galaxy born small and dense. It's a survivor, the relic core of something that was once grander, whittled down to its most resilient piece by an encounter with a behemoth. The other idea is that they formed this way from the start. That in the early universe, some clouds of gas collapsed with such ferocious intensity that they forged these ultra-dense stellar spheres directly, skipping the phase of building a large, extended structure. That would make them a rare, primordial class, but regardless of how they were born, the environment inside one is nothing like our own quiet galactic neighborhood. With stars packed so close together, the gentle dance we see becomes a crowded scramble. Close gravitational encounters between stars are common. Binary star systems can get disrupted. And planetary orbits, if they even exist there, could be thrown into chaos by the constant gravitational nudges from passing stars. It's a stellar ecosystem of intense interaction. Studying these dense enigmas helps astronomers understand the limits of galactic structure. They represent one extreme of the cosmic density scale, a place where gravity won, compressing an island of stars into its most concentrated, fierce form. A compact testament to the shaping power of either a violent past or a uniquely intense beginning. A brilliant green dot, that's what they saw, just a dot. In these wide, dark fields of distant galaxies, some people volunteers, part of the Galaxy Zoo project, they noticed something odd, small, compact, and this very clear green color. They named them green Pea Galaxies. That color, it isn't coming from stars. It's a chemical signal. That bright green glow, it's from doubly ionized oxygen gas. Gas that's been heated up intensely. These are small galaxies, only a few thousand light-years across, but they're erupting. They're forming stars for their size, hundreds of times faster than our own Milky Way does. This furious burst of creation, it makes massive, hot stars, and those stars flood everything around them with ultraviolet radiation. That radiation hits the oxygen gas around them, excites it. And that's what makes it shine with that specific electric green. We see them a few billion light-years away, so we're seeing them as they were a few billion years in the past. They're not from the very first beginning, they're from a later chapter, a crucial one, and that's why they're more than just a curiosity. They're considered our best local examples. For the galaxies that changed everything, because in the first few 100 million years after the Big Bang, the universe was a fog, a sea of neutral hydrogen gas. It scattered light, made everything opaque, then something happened. Something flooded the cosmos with high-energy ultraviolet radiation, enough to rip electrons away from all those hydrogen atoms. This process is called reionization. It cleared the fog. It made the universe transparent to light. Let the first galaxies be seen across huge distances. But what created that flood of radiation? The main candidates are small, compact galaxies. Galaxies forming stars intensely, pouring out UV light from countless new, massive stars. Galaxies that look and act almost exactly like the green peas we see closer to us. So studying these nearby green peas, it gives us a front row seat to the physics of that transformative time. We can measure their gas, their star formation rates, how much radiation they leak out into the space between galaxies. They're a living laboratory, a time capsule, letting us test our ideas about one of the most important changes in cosmic history. So that faint green dot found by a volunteer looking at an image online, it becomes a direct link. A signal from a nearby galaxy that echoes the processes that shaped the entire visible universe. It reminds you that the keys to the deepest past, they're sometimes hidden in the most unassuming places. And vividly colored, a green dot means a busy nursery, but some of the biggest construction sites in the cosmos are hidden. There are galaxies we can't see. Not with our eyes, not with optical telescopes. They're completely hidden behind curtains of their own making. But if you look with a different kind of eye, one that sees in submillimeter light, a kind of far infrared, then these hidden giants come into view. They're called Submillimeter Galaxies. They're the dusty powerhouses of the young universe. At these wavelengths, you're not seeing starlight, you're seeing the glow of warmth. Imagine a galaxy forming stars, not just quickly, at a rate that's hard to believe. Thousands of times faster than the Milky Way. Every year, it might make 1,000 new suns. This isn't a starburst, it's a hyperburst, a firestorm of creation. But all those new stars are born inside thick clouds of dust, tiny grains of silicate and carbon, made in older stars and blown out into space. The dust is so thick it absorbs almost all the visible light. The ultraviolet light, it's like a cosmic blanket. The energy doesn't vanish. It gets absorbed by the dust grains. It heats them up to a few tens of degrees above absolute zero. And those warm grains re-radiate the energy, but at much longer wavelengths in the submillimeter. So what we see is not the fire, it's the warm glow of the smoke around it. These objects are incredibly distant. We see them as they were when the universe was only a few billion years old. They're snapshots of a brief phase. A galaxy-building frenzy. Astronomers think these dusty monsters are the direct precursors to the giant elliptical galaxies we see nearby. Think about that. A submillimeter galaxy is in its most intense, dusty phase. It's assembling stars at a breakneck pace. Then it runs out of gas, or maybe the energy from all those stars blows the gas and dust away. The dust settles, the star formation stops, and what's left is a vast, smooth sphere of ancient stars, a giant elliptical. The most majestic, quiet giants today began their lives in these shrouded, violent factories. Their discovery changed things. For a long time, we thought the early universe was dominated by brilliant, blue galaxies, the ones we could see in optical light. But the submillimeter galaxies revealed a parallel population, a hidden half of the story. Some of the most massive galaxies were building themselves in secret. Behind these veils, it's a reminder that our view is limited by our tools, by the light we choose to see, the most transformative events where galaxies define their destinies might be playing out in the dark. They require us to listen to a different signal, to feel for the warmth in the shadows, and in doing that, uncover the true scale of creation in the ancient universe. That warm dust glow is one kind of nursery, but the early universe had a different light, a soft, immense glow, a kind of cosmic fog lamp. They're called Lyman alpha blobs. These enormous clouds of primordial hydrogen gas, some over 300,000 light-years across, and they shine with a specific color, a deep ultraviolet wavelength, Lyman alpha. It's the fingerprint of hydrogen, the most basic element, getting excited and releasing that energy. But the scale is the mystery. What lights up a gas cloud bigger than a galaxy? The answer isn't one source, it's a chorus of creation inside the cloud itself. When you look into one of these giants, you often find not one galaxy, but several. Dozens of young, frantic starburst galaxies, forming stars at a ferocious rate. The combined ultraviolet light from billions of new, hot stars floods the hydrogen fog. It excites the atoms, the whole vast cloud fluoresces, like a cosmic neon sign powered by stellar birth, but starlight might not be the only source. Some of these blobs also contain brilliant quasars, the furious cores of supermassive black holes, shining with the power of 100 galaxies. That intense radiation could also light up the nebula. Or it could be something more fundamental, a process called gravitational cooling. As vast rivers of cold gas flow along the cosmic web, they pour into an immense dark matter halo. The gas crashes together, it shocks, it heats up, and as it cools down again, it releases that energy as Lyman alpha light. That would mean the blob isn't just a container. It's the main event, a giant dark matter halo gathering its first massive infusion of gas, glowing with the heat of that assembly. Whatever the exact trigger, their significance is profound. A Lyman alpha blob is not a single galaxy. It's a cradle, a protocluster. We're seeing the construction site for the largest structures in the cosmos. An entire galaxy cluster with hundreds or thousands of galaxies in its earliest stages. The glowing hydrogen is the raw material, the reservoir for all those future galaxies. Inside that soft, immense glow, the great metropolitan centers of the future universe are just beginning to spark. They show us the universe doesn't build its largest structures one galaxy at a time. It weaves them together from vast sheets and filaments of gas. It lights up the dark with the soft, monochromatic glow of hydrogen as the first foundations are laid. The universe keeps some secrets close. There's this idea, a kind of phantom in the whole cosmic picture, a galaxy that's almost not there, a dark galaxy. It's a prediction, a logical outcome of how we think dark matter works, how galaxies form, but it's a shadow. We've barely seen a hint. The idea is simple. Profound, really. Imagine a huge halo of dark matter. It gathers a massive cloud of primordial hydrogen gas, just like all the others did early on. But then, for some reason, that gas never ignites. It never collapses into those dense knots to spark the first stars. The switch never gets flipped. You'd be left with this immense structure, a gravitational entity with the mass of a true galaxy. But made of darkness and cold, neutral gas, a ghost with no light. The stellar fireworks just never start. For decades, these have been theoretical phantoms. Necessary for the models, but maddening to actually find. How do you see something meant to be invisible? Astronomers hunt by looking for the one thing that might give it away, that vast reservoir of cold hydrogen. They scan with radio telescopes tuned to the frequency neutral hydrogen emits, and they've found curious things, isolated clouds of hydrogen floating in intergalactic space with no visible stars to explain them. One famous candidate is a cloud called HI1225+01. It's a massive blob of hydrogen with the gas content of a small galaxy. But when you point the most powerful optical telescopes at that spot, you see nothing. Just darkness, the deep black of empty space. It's a compelling hint, a whisper, but proof. The challenge is there are other explanations. It could be a tidal tail, gas ripped from a visible galaxy during an encounter, now so faint the stars are undetectable. Or a cloud that's just too diffuse, its stars too spread out for our instruments to resolve. So the hunt continues. The potential existence of true dark galaxies pushes at the limits of our detection. It asks a fundamental question. What are the minimum conditions to light the first star? Is there a critical density, a specific trigger, without which a cloud of gas just drifts forever in the dark? Finding one would be more than a new catalog entry. It would open a window into a road not taken, a parallel cosmic history where the lights never came on. It would show us the pure scaffolding of the universe before the decoration of starlight. They represent the ultimate frontier, not the brightest or most bizarre, but the most elemental. Foundations that chose, for reasons we don't yet understand, to remain in the quiet dark. Even among the compact objects, you get misfits, things that just don't fit the labels. In the centers of galaxy clusters, there's a whole class that doesn't belong. They're called ultra-compact dwarfs, and they're stuck in this middle ground. Too heavy to be a star cluster, too small to be a real galaxy. They're these stellar puzzles. Look at M60, that big elliptical galaxy. Around it, astronomers saw these tiny, bright points. At first, they thought they were just foreground stars or maybe globular clusters, those old spherical swarms that orbit galaxies, but the data was different. These points were far too bright. When you broke their light into a spectrum, it showed they had millions of stars, sometimes hundreds of millions, all crammed into a sphere maybe 200 light-years wide. That density is extreme. A true globular cluster might have a few 100,000 stars. An ultra-compact dwarf has 1,000 times that mass in a space not much larger. They're like stellar cities crushed down to a single point. So what are they? Where do they come from? It seems the universe has two ways to make them. The first is a story of loss. Imagine a small dwarf galaxy, one with a dense core, drifting into the harsh environment of a galaxy cluster. Those same tidal forces that can strip a galaxy's outer layers to make a compact elliptical, they could work here on a smaller scale. They could strip away the entire fluffy halo of the dwarf, leaving behind just its incredibly dense, star-packed nucleus. In this view, an ultra-compact dwarf is an orphaned galactic core. The ghostly heart of a galaxy that was completely taken apart. The second recipe is about building up, not whittling down, but aggregation. In places of intense star formation, like the Anemic galaxies, you get superstar clusters. These are huge clusters born from galactic collisions. Now, what if several of these superclusters, born close together, later merged? Their combined gravity could pull them into one, even more massive object. So an ultra-compact dwarf could be the product of a merger of giants, a stellar metropolis built from several brilliant towns. Their existence really challenges our catalog. For a long time, astronomy had a simple split. Over here, star clusters bound by gravity but with no dark matter halos. Over there, galaxies, each one anchored by its own massive dark matter halo. Ultra-compact dwarfs blur that line. Some studies suggest they might have significant dark matter, like a true galaxy. Others suggest they might not, like a colossal cluster. The answer might not be the same for all of them. They might come from both paths, and that's the lesson they offer. The universe doesn't use our neat categories. It creates gravitationally bound structures across a whole spectrum, from a few hundred stars in an open cluster, to millions in a globular, to hundreds of millions in an ultra-compact dwarf. to billions in a dwarf galaxy and trillions in a giant. There's no hard boundary, just a smooth gradient of scale. The ultra-compact dwarf reminds us that our need to classify and name is our own. The cosmos just builds in endless variation, filling every possible niche of size and mass with something luminous, bound by gravity. They're the ultimate misfits, and by defying our labels, they show us the continuous creativity of the universe. After that whole journey through all the different kinds of galaxies, we come back to our own. The barred spiral, we saw others in that category, like NGC 1300, but the quiet fact is no two are exactly alike. The Milky Way is its own thing. Its central bar is a certain length, not too long, not too short. It's a bridge of stars between the inner and outer parts. The layout of its spiral arms, the Perseus arm, the Scutum Centaurus arm, the Norma arm, that's a pattern you won't find anywhere else. And our collection of satellite galaxies is specific too. The large and small Magellanic Clouds, other dwarfs, each one points to a past gravitational event. And then there's our merger history. That's a unique fingerprint. The Gaia spacecraft found streams of stars in our halo. They're the leftovers from smaller galaxies we absorbed long ago. Like the Gaia Enceladus galaxy, which probably merged with us around 10 billion years ago, that layered past is ours alone. So knowing the 29 other types, it doesn't make our home smaller. It puts it in context. It shows us the common processes, the mergers, the bar formations, the tidal stripping, the star formation bursts. These are the things that shape all galaxies. But they also show the infinite variations, the specific angles of a collision, the exact amount of gas available, the timing of events, the quirks of spin. All of that guarantees that every galaxy, even in the same class, becomes a one-of-a-kind object. The Milky Way isn't some solitary archetype, it's a sibling. One voice in a huge chorus of barred spirals, but its song made from its particular stars, its specific history, and the life that's emerged inside its disk. That song is only sung here. Our home is special, not because it's the only one of its kind, but because it's ours, a singular point in the grand, evolving gallery of the universe. The universe has this incredible way of shaping things. You see these serene, smooth ellipsoids from ancient stars, and then you have these violent rings where stars are born. We looked at 30 types of galaxies. The diversity is staggering, the creativity. Every shape tells a story of birth, of gravity pulling and pushing, of evolution across billions of years. Those calm, giant ellipticals, they speak of ancient mergers, titanic events, and the perfect ring galaxies. They're like a frozen moment. A single, piercing collision captured in time. Then you have the faint ones, the ghostly, ultra-diffuse galaxies. They whisper about dark matter halos. Halos that never gathered enough light, and the frantic blue compact dwarfs. They echo something. They echo the universe's very first dawn. This exploration, it does more than just catalog curiosities. It shatters something. It shatters the idea that our Milky Way is the standard, the archetype for all islands in the void. It's not that. It's just one verse. One exquisite, complex verse in a much larger poem, a cosmic epic that's still being written. Our home is a single design, one design in a gallery of infinite possibility. That perspective, it changes everything. So the next time you look up, you see that hazy band of light arching across the dark. See it anew. Don't see it as the only possible galaxy. See it as our local address, one point of light in a vast tapestry. A tapestry woven from trillions of stars, shaped by gravity, by time, by chance. Let that deeper understanding settle in. Let it deepen your wonder every time you gaze at the night sky. The universe isn't a place of repetition. It's a workshop of endless invention.